Hello everyone, I am Avantika Agarwal. Today I will be talking about oracle separations for the quantum classical polynomial hierarchy. So let me start by talking about the classical polynomial hierarchy and what we know about it, and then I'll talk about the quantum classical setting. So the classical polynomial hierarchy, or PH, is an infinite hierarchy of classes whose zeroth and first levels are the well-known complexity classes P and NP. So in this talk, we'll think of P as follows. So suppose we have a judge who is an efficient classical computer, and this judge is trying to solve some yes-no problem. So the judge gets some input X, it performs some efficient classical computation, and outputs yes or no. And this gives us the complexity class P. Now we'll think of NP as follows. So again, we have a judge who is an efficient classical computer, and now we have a debater dy who is trying to convince the judge to say yes. So together they are trying to solve some yes-no problem. So they get some input X. The debater dy sends a message to the judge. The judge performs some classical computation, efficient classical computation, and outputs yes or no. So we want that if X is a yes input, then there is some message that dy can send to the judge such that the judge outputs yes. On the other hand, if X is a no input, then we want that no matter what dy tells the judge always outputs no. Now, instead of considering this debater dy, whose aim is to try and convince the judge to say yes, we could have considered an alternative debater dn, whose aim is to try and convince the judge to say no. And this gives us the different complexity class called co-NP. So now what's happening? Again, we have this judge who is an efficient classical computer, and we have a debater dn who is trying to convince the judge to say no. Together, they're trying to solve some yes-no problem. So now they get some input X. Debater DN sends a message to the judge. The judge performs some efficient classical computation and outputs an answer. So we want that if X is a yes input, then no matter what the debater DN tells the judge always outputs yes. On the other hand, if X is a no input, then we want that there is some message the debater DN can tell the judge so that the judge outputs no. Now, instead of considering these classes NP and co-NP, where the judge just talks to one of these debaters, we can start to consider bigger complexity classes of problems which can be solved using an I-round debate between the two debaters. So this gives us the ith level of polynomial hierarchy. So again, now what is the setup? We have this judge who is an efficient classical computer, and we have the debaters dy and dn. Dy is trying to convince the judge to say yes, and dn is trying to convince the judge to say no. And they send I messages alternately, at the end of which the judge performs some efficient classical computation and outputs yes or no. So now that we have two debaters, we have two choices of which debater speaks first. If dy speaks first, then we get the complexity class sigma I. And if dn speaks first, then we get the complexity class pi I. And together, sigma I and pi I form the ith level of the polynomial hierarchy. We can also see that the ith level of pH contains the I minus 1th level of pH, because the judge can just ignore a message from one of the two debaters, and that makes it an I minus 1 round debate. So now using this, we can define our polynomial hierarchy. The 0th level is P. The first level is NP and co-NP. The second level is sigma 2 and pi 2, and so on. And now I have drawn all these complexity classes distinctly on this page for a reason. It's because we believe that these classes are different, just like we believe that P is not equal to NP. Now, we also have some evidence for believing it using something called the collapse property of pH. So it seems natural to believe this because we should be able to solve more problems if we are allowed more rounds of debate. And the collapse property of pH tells us that suppose you believe that 5 rounds of debate and 6 rounds of debate give you the same amount of power, then that means that 5 rounds of debate and 500 rounds of debate should also give you exactly the same power. And that we should find a bit hard to believe. We should be able to solve more problems using 500 rounds of debate than we can using 5 rounds of debate. So, okay, so we believe that pH is infinite, but can we actually show this? So let's start with the simpler question. Can we show that P is not equal to NP? So it turns out that in general, we do not know how to show such results. But in the Oracle model, we can show such results. So let me tell you what the Oracle model is, and then I'll tell you what we can show. So in the Oracle model, our computers are given some extra power. So we have here M, which is a classical computer, and it's trying to compute some function G. Now it's given some extra power using an oracle. So we have this oracle which contains some function f inside it, and M has access to this oracle. So during its computation, M can make some queries to this oracle. So it sends a query y to the oracle and it gets the response f of y in a single time step, even if this function f is hard to compute. So it gets some input x, performs some computation. During its computations, it makes queries to the oracle and then finally outputs the answer g of x. So now we want to understand that with this extra power, what functions this computer M can compute efficiently and so on. So for example, if M computes G in polynomial time when given oracle access to F, then we say that the function G belongs to the complexity class P with oracle access to F. So just to make sure we are all on the same page, what does PH with an oracle look like? So recall we had this judge and two debaters who were sending messages to the judge. So now this judge has oracle access to the function f. So it gets these I messages from the debater. Then it performs some computation. During its computation, it can send queries to this oracle f and use that to finally make its yes or no decision. So now what can we show in the oracle model? Well, in 1975, Baker, Gill, and Soloway showed that there exists an oracle O such that P is not equal to NP. And then it was an open question whether there also exists an oracle O such that pH is infinite. So this was resolved in 1986 by Hofstad, who showed that yes, that is indeed the case. So there exists an oracle O such that all of pH is infinite. So that means that there is some problem that the I plus 1th level of pH can solve, that the ith level of pH cannot solve. And this is true for every I. But both of these oracles, the Baker-Gill-Soloway construction as well as the Hofstad construction, was a very contrived oracle construction created just for the purpose of showing that P is not equal to NP or pH is infinite. So then it's natural to wonder whether you need all the structure in your oracle in order to be able to show such a result, or whether you can also show such a thing for an unstructured oracle. So what do I mean by an unstructured oracle? So in this talk, we'll model an unstructured oracle using a random oracle. So what is a random oracle? So recall we had in the oracle model, we had this oracle which contains some function f inside it. So now for the random oracle model, this function f is now sampled randomly on all input. So M will send some query y to this oracle. The function f will output a uniformly random 0, 1 bit for the value f of y. And now in this oracle model, we want to know whether pH is infinite. Because this oracle is random, it's clear that it does not have any structure that is specific to either P or NP or polynomial hierarchy or any other complexity class. So now with this unstructured oracle, what can we say? So this was an open problem in Hofstad's work in 1986, whether pH is infinite relative to a random oracle. And it was resolved relatively recently in 2017 by Hofstad, Rossmann, Servideo, and Tan, who showed that with probability 1, pH is infinite relative to a random oracle. So that means that with probability 1, if you're sampling a random oracle, then there is something that the I plus 1th level of pH can solve, that the ith level of pH cannot solve. So that is all I had to say about classical pH for now. So now let's talk about the quantum classical analog. And let's start by talking about how you would define a quantum analog of NP. So recall what was NP? We had this judge who was an efficient classical computer, and we had the debater DY who was sending a classical message to this judge. Now, to define a quantum analog, there are two things here that we can make quantum. One, we can replace the judge by a quantum judge. Two, we can replace the message that the debater DY is sending by a quantum message. So for this talk, we choose to let the message remain classical and replace the judge with a quantum judge. And this gives us the complexity class QCMA, quantum classical Merlin Arthur. So we have a quantum judge who is receiving a classical message from the debater DY. So now what is the setup? We have this quantum judge. So it's an efficient quantum computer. And we have the debater DY who is trying to convince this judge to say yes. So DY will send some classical message to the judge. The judge will perform some efficient classical quantum computation and output a yes or no answer. We want that if X is a yes input, then there exists a message that DY can send to this quantum judge so that the judge outputs yes. If X is a no input, then we want this no matter what message this DY sends to the judge always outputs no. And similarly, now we can define the quantum classical analog of the ith level of pH. So we can define the class QC sigma I, where again, now we have a quantum judge. So this is an efficient quantum computer who is receiving I alternating messages from the two debaters DY and DN. So there's I rounds of classical debate, after which this efficient quantum judge will make a decision. Similarly, we can define QC pi I if the debater DN speaks first. We can also note that the classical polynomial hierarchy is contained inside the quantum classical polynomial hierarchy. So think of the class pi I. We can see that it's contained in QC pi I because a quantum judge can just choose not to use its quantumness and just perform some efficient classical computation. So now we can define our quantum classical pH. So BQP is the 0th level, the class of problems which can be solved by an efficient quantum computer. The first level is QCMA and QCMA, second level is QC sigma 2 and QC pi 2, and so on. And like we said earlier, the ith level of classical pH is contained in the ith level of quantum classical pH. Again, just like we believe that the classical pH is infinite, we also believe that the quantum classical pH is infinite. And we have further evidence for this belief because of the collapse property for QCPH. So this tells you that, okay, now you have a quantum judge and some I rounds of debate. So it tells you that if now 5 rounds of debate and 6 rounds of debate have the same power, then once again, 5 rounds of debate and 500 rounds of debate have exactly the same power. And that we should find a bit hard to believe once again. So now can we show that QCPH is infinite? Again, like the classical setting, we do not know how to show this. So then it's natural to wonder whether we can show this in the oracle model. So does there exist an oracle O such that QCPH is infinite? And if there does exist an oracle O such that QCPH is infinite, then do we need a lot of structure in this oracle to be able to show this result? Or can we also show this for an unstructured random oracle? So this brings me, again, just to make sure we're all on the same page, what does QCPH with an oracle look like? So now we have a quantum judge and these two debaters DY and DN. And this time, this quantum judge has oracle access to the function f. So what does that mean? So during its computation, the quantum judge can make queries to this function f. But now, since this judge is a quantum judge, it can make queries to f in superposition. So it can send a superposition of inputs and get a response from the oracle in superposition. So now let's see what our main results are. So we show that indeed in the oracle model, QCPH is infinite. Most strongly, we show that with probability 1 relative to a random oracle O, QCPH is infinite. So we do not need a lot of structure in the oracle to be able to show this result. Moreover, we show that relative to a random oracle, no fixed level of QCPH contains all of pH. So what does that mean? Well, recall this diagram we made from earlier, where we said that the ith level of classical pH is contained in the ith level of QCPH. But what about the I plus 1th level of classical pH? Is that also contained in the ith level of quantum classical pH? So we show that relative to a random oracle, this is not true. So there exists, for every level I, there exists some problem that the I plus 1th level of classical pH can solve, that the ith level of quantum classical pH cannot solve. Okay, so now let me talk about how such an oracle separation is shown. And once again, let me start by talking about how we show oracle separations for classical pH. And then I'll talk about what we do in the quantum classical setting. Okay, so how to show oracle separations for classical pH? Well, in 1984, first Sipser and Sachs gave a connection between oracle separations for pH and circuit lower bounds for constant depth circuits. So they gave a recipe using which if you can show circuit lower bounds for constant depth circuits, then their method will also give you oracle separations for pH. So what does that mean? So let's look at some sigma I protocol in PH. So we have this judge, two debaters, and I rounds of debate. So first, Sipser and Sachs convert this protocol into a classical circuit of depth I. So this circuit has AND and OR gate, so alternating layer of AND and OR gates, and it has depth I. And then they say that, okay, now if for this depth I circuit, you can show a circuit lower bound, then we will give you a method to show an oracle separation for sigma I. So now we can forget about judges and debaters and protocols and just focus on showing strong enough circuit lower bounds. So we want to show that something is hard for these depth I circuits. So now how do you show such a thing? How do you show any type of circuit lower bounds for constant depth circuits? Well, one method that is very useful to be able to do that is what's called the random restriction method. And it says the following. So it says that after applying a random restriction, a constant depth circuit simplifies. So there are two things I need to explain here. What is a random restriction and what do I mean by a circuit simplifying? So let's start by looking at random restrictions. And let's start by just looking at what is a restriction. So suppose we have some function f, it takes some input x and outputs f of x. So now what is a restriction of f? So a restriction row of f is we'll take some input bits of f, set them to some fixed 0 and 1 values. And now how do we evaluate this restricted function? So it takes a smaller input x, which is then input into the unrestricted variables of the original function f. Now this original function f is evaluated on this larger input, and the output of this original function f on the larger input is how we evaluate a restricted function. So that's how we get f sub rho of x. So now what is a random restriction? Well, strictly speaking, a random restriction is any random distribution on the arbitrary restrictions we just discussed. But we will be interested in a specific type of random restriction. So how do we sample our random restrictions? So again, we have this function f and we are trying to apply a random restriction to it. So first, we'll sample some input x to this function f from some distribution d. So we have sampled this input x1 to xn from the distribution d. And now, for every input bit of this function f, we'll either leave it unrestricted with probability p. So we'll suppose we are looking at the second bit, we'll set it to star, leave it unrestricted with probability p, and we'll restrict it with probability 1 minus p. If we choose to restrict this bit, then we'll restrict it to the value that the input x we sampled tells us. So if we are looking at this ith bit and we chose to restrict it with probability 1 minus p, then we'll set it to the value x sub I from the input that we sampled. And we do this independently for every bit of the input of the function f. So every input bit independently, you leave it unrestricted with probability p and you restrict it with probability 1 minus p, in which case you set it to a value that is told to you by this input x you sampled from the distribution. So these are our random restrictions. And now, what do we do with this random restriction? So the random restriction method says that after applying a random restriction, an AC0 circuit simplifies. So these types of results are called switching lemmas in classical complexity. So what does it mean? So it means that suppose you have some depth 2 circuit here and you apply a random restriction to it, then Hofstad's switching lemma tells you that with very high probability over the choice of this random restriction, uh, your depth 2 circuit will become a small depth decision tree. And we know that small depth decision trees are a very weak model of computation for which we know how to show lower bounds. So it's a simple model of computation where we know how to show lower bounds. And that's what it means for this depth 2 circuit to simplify. So we applied a random restriction, and with very high probability over the choice of this random restriction, the depth 2 circuit simplified to a small depth decision tree. So now we'll use a similar method for the quantum classical polynomial hierarchy. So now we have, suppose, some QC sigma I protocol. So we have a quantum judge uh, who receives these I messages from the two debaters, and then it makes a decision. So we can convert these QC sigma I protocols into a different type of circuit, which we call QAC0 circuit. So what do these circuits look like? So first, the circuit has a classical circuit of depth I. So this classical circuit contains alternating layer of OR and AND gates for depth I. And this is followed by a layer of quantum query algorithms. So these quantum query algorithms come from the fact that a judge is now a quantum judge. And we call these QAC0 circuit. So a depth I classical circuit followed by a single layer of quantum query algorithms. And then using a method similar to first Sachs and Sipser, we can say that, okay, if you can show strong enough circuit lower bounds for this class of circuits, then you will also be able to show an oracle separation for QC sigma R. So now we want to show circuit lower bounds for these QAC0 circuits. And this brings me to our main technical lemma. So we show a quantum switching lemma. So what does that mean? We show that after applying a random restriction, a quantum query algorithm simplifies. So suppose we have this green quantum query algorithm here, which is making a bunch of queries to some input. Then if we apply a random restriction to it, then with very high probability under the choice of a random restriction, this quantum query algorithm becomes close to a small depth decision tree. So which means that it simplifies because now we know how to show lower bounds for these small depth decision trees. Note that there's one crucial difference from the classical setting. So this quantum query algorithm will only become close to a small depth decision tree, which means that the small depth decision tree can make an error on some inputs, but the number of those inputs will be very small. And using this quantum switching lemma, we can show circuit lower bounds for the QAC0I circuits that we described. And that gives us oracle separation for the quantum classical variant of polynomial hierarchy. In fact, we show something a little bit stronger. So we show that our switching lemma also works for low degree polynomials, which as a corollary implies that our switching lemma works for quantum query algorithms. So that is all I had, and thank you.